What's up everybody, welcome to another video. Hope you're ready to flex those brain muscles. In this video I'm going to talk about the Intermediate Value Theorem, and I'm going to focus on understanding the theorem conceptually, understanding the formal statement of the theorem, and then applying it to different examples. Let's jump right into a task focused on gaining conceptual understanding. Here's a function, but I have some of the function covered up, this middle portion between -2 and 2. Does this function have to have an x-intercept between -2 and 2 in this covered portion? So as 3 blue, 1 brown would say, pause and ponder. Think about this. All right, hopefully you paused and thought about this. When I showed my students, I had some students say, yes, the function's linear. It looks like this and it crosses the x-axis. I had other students say, well, no, it doesn't necessarily have to. It could have a jump like this and it could just jump over the x-axis. I had other students say it could have a hole. It could be undefined at 0. Means it just skips right over the x-axis. It's undefined, it doesn't have an x-intercept. Or it could be something crazy like this where it has asymptotes and it shoots down and shoots up and doesn't cross the x-axis at all. So going back to our original question, does this function have to have an x-intercept between -2 and 2? If this is all the information I give you, then the answer is no, it doesn't have to, because we could have a situation like one of these three that I just showed. Right? So what condition, here's the question, what condition, what could I tell you about this function that would guarantee that it does intersect the x-axis between -2 and 2, that it does have an x-intercept? And it's helpful to think about the examples where it didn't, right? One example had a jump, another had a hole, another had an asymptote. What are these all examples of discontinuities, right? So it turns out that if I told you this function was continuous along with showing you this, then you would be able to conclude that at some point between -2 and 2 it had to cross the x-axis, even if it's not linear, not a line, even if it's, you know, curved like this in between. It still at some point has to cross in order to connect from here to here without picking up our pencil. Okay, so continuity, this is a key idea of intermediate value theorem. Here's another key idea. Now here's a different function, and now I'm telling you that it's continuous, so no jumps, no holes, no asymptotes. Does this function have to have an x-intercept between -2 and 2? And when I showed students this, they quickly said no. And they said it could look just something like this, and it could connect like that and not touch the x-axis at all. That's absolutely correct. Could do something weird, but it doesn't have to. So why not? I'm telling you it's continuous. What's wrong with this example? And this has to do with this idea of betweenness. And I think I just made that word up, but being between, right? X-axis means y equals 0. What are the y values of these endpoints? Well, we don't exactly know them because the units aren't shown, but we know that they're both bigger than 0. And so 0 is not between the y values of these endpoints, so we do not have to cross through it in order to connect these two endpoints. So two key ideas behind intermediate value theorem: continuity and betweenness, that lead us to this theorem. So before you read the theorem, let's just explain kind of what we learned in simple terms, which is that if we have a continuous function, if it's continuous on some interval from a to b, then the function has to pass through every single y value between f of a and f of b. It has to. There's no way to connect these two dots without passing through every single y value between f of a and f of b. It could pass through some more than once. Could do something like this, right? It could extend beyond these y values, like it could go down, then go way up. Those are absolutely possible, but what can we guarantee from this theorem? And that's just that it passes through every single one at least one time. So how do we write this into a formal mathematical theorem? Well, it's right here. If f is a continuous function on the closed interval ab, and k is a number between f of a and f of b. So let me just draw an example function. K is any number between f of a and f of b, so k is a y value. Let's write it here. This is an example of some k, right? So if these two things are true, continuous and k is between these two y values, then there must exist a number c between a and b. So c is an x value. There must exist a number c such that f of c equals k. That means we plug c into the function and we get k, or c is the x value that corresponds to this y value k. Hopefully that's making sense. Let's practice applying it in different examples. And the focus on these first three examples is just figuring out, can we apply the theorem or not? So again, two things we're focusing on: continuity and betweenness. So let's look at this first one. Can we use the IVT to conclude that this function has an x-intercept between 0 and 2? So what does it mean for a function to have an x-intercept between 0 and 2? That means there has to be a solution to this equation, f of c equals 0, where c is between 0 and 2, right? So the y value in this case, or the k that was in our theorem, is 0. And we're trying to figure out, is there a value c we can plug in between 0 and 2 that gives us 0 for the y value? How do we figure this out? Well, first, continuity, that first condition. Is this function continuous on this interval? Let's check. This is a rational function. It potentially has discontinuities, holes, asymptotes, and those come from the denominator. Any number that makes the denominator equal to 0 is a discontinuity. Let's see, I only see one of those, and that's when x equals 1. The denominator is 0. So now we have to think, is 1 between 0 and 2? Is it in this interval? It absolutely is. So this function is not continuous on the closed interval 0, 2. So no, we cannot apply the intermediate value theorem. Now, does this mean that there's not an x-intercept between 0 and 2? No, right? It just means that we can't conclude whether there is or isn't. I want to make that clear. We cannot conclude that there isn't an x-intercept between 0 and 2. We just can't conclude whether or not there is. Hopefully that makes sense. All right, next example. Given this same function, can we use the IVT to conclude that there exists a number c between 2 and 4 such that f of c equals 1? So now our y value is 1. Our x values are 2 and 4, so we're looking at this closed interval here from 2 to 4. And so our first step is continuity. Is the function continuous on this interval? And it is. The only discontinuity is at 1, and that's outside of this interval. So we're good with continuity. Now we check the next condition of betweenness. Is 1 between f of 2 and f of 4? Let's evaluate each of these. F of 2 is equal to 2 squared is 4, minus 2 times 4, that's 8, plus 1, over 2 minus 1 is 1. Let's see, negative 4 plus 1, negative 3. So this equals negative 3. That's f of 2. And now I want to figure out f of 4. What is f of 4? 4 squared is 16, minus 4 times 4, which is 16, plus 1. So that numerator is going to equal 1. And then 4 minus 1 is 3. So f of 4 equals 1/3. Is 1 between negative 3 and 1/3? It is not. So we cannot conclude that there exists a number c between 2 and 4 such that f of c equals 1. No, we can't conclude. Again, that doesn't mean that there isn't, just means we can't conclude whether or not there is using the IVT. Finally, can we use the IVT to conclude that there must be a solution to this equation on the interval 2, 4? All right, now all of a sudden we're talking about equations, and before we've been talking about functions. These things are very related, although it may not be obvious at first. How can we think about this in terms of the IVT, like function values? Well, if we have a function f of x equals this expression here, just like what's written here and here, then what would it mean? How can we relate that to this expression equals 0? Well, that's just an x-intercept, right? That's y equals 0. When does f of x equal 0? So we're trying to figure out, is there a solution to this equation f of c equals 0 where c is in this interval from 2 to 4? It's essentially the exact same thing that number 1 asks us with a different interval and worded differently. Hopefully that makes sense. All right, so continuity from 2 to 4. Are there any discontinuities? No, we found the only one is 1, so we're good to go there. And we actually already found the endpoints as well, negative 3 and 1/3. So now we're just checking, is 0 between negative 3 and 1/3? And it is. So we've met both conditions. We have continuity, we have betweenness. So yes, we can conclude that there must be a solution to this equation on this interval, or alternatively, this function has an x-intercept between 2 and 4 according to the intermediate value theorem. Hopefully this is making sense. Let's do a check for understanding. I asked my students this on a quiz. Pause the video, try this multiple choice problem on your own, play the video to check your answer. All right, hopefully you got an answer. Let f be a continuous function on this closed interval from negative 1 to 3, and it gives us the y value of the endpoints, -2 and -5. Which of the following is guaranteed by the intermediate value theorem? If you're struggling with this, what I very much recommend is drawing a graph like this, right? So we are looking from the interval from -1, so I'll put -1 over here, to 3. Those are x values. This is really important with IVT, is coordinating the difference between x values and y values. F of 1 is -2, and f of 3 is down here at -5. Okay, so f of -1 is -2, f of 3 is -5, and what the IVT tells us is that this function has to pass through every single y value between -2 and -5 as it moves from -1 to 3 across the x-axis. All right, so let's go back to our multiple choice answers. The y value has to be between -2 and -5. We can automatically eliminate c, and we can eliminate b, because this is saying f of c equals 0. We can't conclude that any y value is 0. 0 is not between the y values of these endpoints, f of a and f of b. All right, what else can we say? Well, we can say that there is a solution to f of c equals -3, where c is between the two x values. C is an x value, right, between -1 and 3. So that eliminates a and allows us to conclude that D is the only one of these four statements that is guaranteed by the intermediate value theorem. So the key idea here is, sort of coordinating the difference between x values and y values. All right, let's jump into two different examples of how we can apply the theorem. And again, one is showing that a function has a 0, a root, or an x-intercept on a particular interval, right? So we are trying to figure out, does this function have a solution? Is there a solution to this equation, f of c equals 0, because that's what it means to be an x-intercept, where c is between 1 and 2. So this is the interval from 1 to 2. So the first thing we're checking again is continuity. Is this function continuous on the interval from 1 to 2, the closed interval? And yes, it is. It's a polynomial. Polynomials are continuous on the set of real numbers. They don't have any discontinuity. So boom, that was pretty easy. We're done with continuity. All right, now what about this idea of betweenness? We're trying to figure out what is f of 1 and what is f of 2, and is 0 between f of 1 and f of 2. So first we'll plug 1 into the function. We get 1 cubed, that's 1, minus 1 minus 1, which is -1. And then we'll plug 2 in. 2 cubed is 8, minus 2 minus 1, which is +5. So 0 is between -1 and 5, and so we conclude that there must be an x-intercept of this function between 1 and 2. Let's write out formally what we can conclude. Since since f is continuous on the closed interval 1, 2, and 0 is between f of 1, which is -1, and f of 2, which is 5, there must exist a value c between 1 and 2 such that f of c equals 0, and this is exactly what it means to be an x-intercept. So in parentheses I'll put an x-intercept between 1 and 2. So I'm just formally writing out a final sentence using the intermediate value theorem and what we can conclude. Hopefully that makes sense. Let's try one more example. This example involved concluding whether there was an x-intercept. The next example is concluding that there's a solution to an equation on a particular interval. So show that this equation has a solution between 2 and 3. How does this relate to a function having a particular value, which is what the IVT states? Well, let's subtract x and add square root of x to both sides of this equation. So we basically get 0 on one side, right? 0 is on the right-hand side now. Now, how can we relate this equation to a function? Well, if I define the expression on the left-hand side of the equation as a function, then how are these related? Well, the first equation is when the function's y value equals 0, which is exactly what we just said an x-intercept means. So we're trying to conclude, does this function have an x-intercept between 2 and 3? In other words, is there a solution to this equation, f of c equals 0, where c is in the interval from 2 to 3? Hopefully that making sense. So we're going to use this function here, and we're going to use the interval 2, 3. We're first going to show continuity, and then we're going to try to show betweenness, that 0 is between f of 2 and f of 3. So let's start with continuity. We're looking at the interval, the closed interval from 2 to 3. Is this function continuous on this interval? This is a little bit tricky, right? This is a weird function. We have a rational piece here, a radical piece here. So we can look at each individual term and figure out, is each term continuous on 2, 3? Because it turns out there's an important theorem related to continuity, which is that if we have a bunch of functions that are continuous on an interval and we add or subtract them together, then the result is still continuous on that interval. So let's go one by one. Where's the discontinuity here? It's at 0. 0 is outside of this interval. This x, this linear term, right, doesn't have any discontinuities. And this square root of x is defined for x greater than 0, greater than or equal to, and it's continuous everywhere on its domain, right, greater than or equal to 0. So we're good here. On the interval 2, 3, this function is continuous, and we've just confirmed that. So now let's show betweenness. What we're going to now show, let me make a little bit of room here, is we're going to try to show that 0 is between f of 2 and f of 3. So let me write this out. What is f of 2? F of 2 equals 2 over 2, that's 1, minus 2, plus the square root of 2. Okay, 1 minus 2 is negative 1, so this is negative 1 plus the square root of 2. And now you could pull out a calculator, but I also know that this is greater than 0. How do I know that? Because I know that the square root of 2 is bigger than 1. How do I know that? Well, the square root of 2 is bigger than the square root of 1 for sure, and the square root of 1 is 1, so square root of 2 is bigger than 1, which means this is going to be positive or greater than 0. So now what I can hopefully show is that f of 3 is less than 0, and then I can use the IVT to conclude that the function has to pass through 0 sometime between 2 and 3, because the y values of the function change signs from positive to negative. All right, so what is f of 3? That is 2/3 minus 3 plus the square root of 3. All right, quick maths here with fractions. 2/3 minus 3. 3 is 9 over 3. 2 over 3 minus 9 over 3 is negative 7 over 3 plus square root of 3. All right, now how do we know that this is less than 0? Well, this is like negative 2 1/3, and I'm adding a number that is less than 2, because the square root of 3 is less than the square root of 4 for sure, and the square root of 4 equals 2. So I'm adding a number that's less than 2 to something that's negative 2 1/3. So the result is going to be less than 0. Hopefully that logic is making sense. So now what's our conclusion statement here? And I'm just going to say it in words because I've kind of run out of room here. Since the function is continuous on this interval and 0 is between f of 2 and f of 3, we can conclude that there must exist a value c such that f of c equals 0, where c is between 2 and 3. Okay? And how does this relate to our original statement? Because if there exists a value c between 2 and 3 that makes this function equal to 0, that's exactly the same thing as being a solution of this equation, which is exactly the same as being a solution of this equation, because they are just rewritten, right? I just moved stuff around. Hopefully that example is making sense. It's about as tricky as it gets, so if this makes sense, you're probably good. Hopefully this video helped. Comment below with any questions, like and subscribe, but most importantly, keep flexing those brain muscles, and I'll see y'all in the next video.